Hello dear grade 12 students, welcome back to my lesson. On today's lesson we are continuing to solving the questions that related with the rotational motion, Newton's second law for rotational motion in section 3, chapter 2. As you know, in a previous lesson we have studied the Newton's second law for rotational motion, which is equal to moment of inertia times angular acceleration. For example, when an object, the net torque, when a net torque acting on an object, okay, so this object, it goes to accelerate, which is equal to the angular acceleration, okay, and the net torque is equal to moment of inertia and time is angular acceleration. So the sign of the net torque, it depends on the sign of angular acceleration. In the case of speeding up, the net torque and angular acceleration becomes positive. In the case of slowing down, such as the effect of the air resistance and the friction, it goes to slow down the object from rotating, and net torque and angular acceleration becomes negative. As you know, in a previous lesson, we stopped it here, question 38, a very good question. So it has been brought in the Wizari exam 2 times, I think. The question says a 12 kilogram mass is attached to a cord that is wrapped around the wheel. So this is the mass of the object attached to what? A wheel, okay, to a cord that's wrapped around the wheel with the radius 10 centimeter. So what is the radius of this wheel? Is 10 centimeter. We have to convert 2 meter divided by 100 is equal to 0.1 meter, as shown in this figure, okay? So the figure must be given in the question. The acceleration of the mass down the frictionless incline is measured to be 2 meter per second square. What is this? This is the acceleration of the mass when it is moving downward from this frictionless incline. Assuming that the axle of the wheel to be frictionless, determine A, the force on the rope. What? The force of the rope, which is directed upward. Okay, this is Ft. And the second unknown, the moment of inertia of what? Of the wheel. The moment of inertia of what? Of wheel. Okay? And branch C, the angular speed of the wheel 2 seconds after it begins rotating start from rest, which means that omega initial is equal to 0. Now, let's solve the first branch, branch A. Okay? Let's open a new page. Okay? Look at this question. We have an incline surface, frictionless. This is rough surface, okay? And this is the mass that attached by a cord or rope, okay? So this is the rope, okay? And this is wheel. The radius of the wheel was given, 10 centimeter. We have to convert 2 meter divided by 100 is equal to 0.1 meter. Okay? So this object, this mass is 12 kilogram. The mass of the object is 12 kilogram. Its acceleration is 2 meter square moving downward. Okay, this is acceleration of the object. Okay, as you know, the force of the rope or the tension force is directed upward. This is Ft. Okay, why? Because this tension force doesn't let the object is moving downward with a very high speed or with a very high acceleration. Okay, but for the incline, if you release an object from the inclined surface, why the object is moving downward without any applied force? For example, if you put the object here, okay, why, if you release this object, why the object is moving downward without any applied force? Because of the gravitational force. But which component of the gravitational force? The perpendicular component, y component, or x component? Absolutely the x component of the gravitational force. It goes to object moving downward. How? Look at this case. As you know, in grade 11, you have learned about the free body diagram for an object on an incline. In this point, the gravitational force is moving downward. Sorry, is acting downward. Gravitational force always downward toward the center. For the inclined surface, this axis becomes x-axis and this is y-axis. Okay, this is for the inclined surface. In the inclined surface, once again, please listen carefully. This axis becomes what? X-axis. And this axis becomes y, becomes what? Y-axis. Okay, so as you know, this gravitational force that acting downward of this object is not on the y-axis, not on the x-axis. Between x-axis and y-axis. So that is why it's going to be resolved into two components. Okay, so this angle is equal to this angle. Okay, so this gravitational force will resolve into two components, FGY and FGX. According to the Pythagorean theorem, because the angle with y-axis, FGY is equal to FG cosine theta. And FGX is equal to FG sine theta. This is according Pythagorean theorem. Cosine theta is equal to hypotenuse over adjacent over hypotenuse. Sine theta is equal to opposite over hypotenuse. Okay, now, how many forces do we have on the x-axis? We have two forces. FGX, which is equal to FG sine theta, and the force, the tension force, the force of the roll. Okay? So the object is moving upward or downward. The object is moving downward in the direction of the FGX. So which one is bigger, FGX or FT? Absolutely, FGX is bigger than FT. Okay? If the FGX is equal to FT, in that case the object becomes stationary, doesn't move. But when FGX is bigger than FT, the object is moving downward. But if FT is bigger than FGX, in that case, the object is moving upward. Okay? So, what is this? This is the normal force. Okay. According to the y-axis, how many forces do we have on the y-axis? Two forces. Fn, Fgy. But these two forces are equal. Fn, is equal to Fgy. So, the summation force on the y-axis is equal to what? 0. Because the object doesn't moving up and down. Okay? Because the object is moving on the surface of the incline, so that is why Fn is equal to Fgy, and the net force on the y-axis, is equal to what? Is equal to 0. But net force on the x-axis is not equal to 0. Fgx is bigger than Ft. Look, net summation force on x-axis is not equal to 0. Fgx is bigger than Ft. According Newton's second law, A to find Ft. Newton's second law says the summation of the force is equal to mass times acceleration. Okay? So, how many forces do we have on the x-axis? Two forces. The summation of these two forces is because these two forces are different in magnitude and different in direction, so that is why we have to subtract. Subtract what? Subtract Fgx minus Ft equal to what? Mass times acceleration. Do we have Fgx? Yes, Fg sine theta. Fgx is equal to what? Fg sine theta, according to Pythagorean theorem, is equal to Ma. Rearrange the equation. Take this Ft to other side, it becomes positive. What is remain? Fg sine theta. Fg sine theta is equal to what? Fg is equal to mg, because gravitational force doesn't given. So, but instead of the gravitational force, mass was given, 12 kilogram, times gravity times sine theta was given. Theta is 37 degree, okay? Sine 37 minus Ft, which is unknown, is equal to mass 12. acceleration 2. Okay, sorry, I rearrange it. I rearrange the equation. Ft is equal to mg sine theta minus ma. Now replace mass 12, gravity 9.81, sine 37 minus 12 times 2. Ft is equal to what? Approximately 47 Newton. The tension force that acting on this object is equal to 47 Newton in this direction. Okay, what is this? This is the tension force that acting on this wheel. Okay, now do we have a force on the wheel? Yes. Do we have radius? Yes. So it means that the torque acting on this wheel is equal to Ft times d. Okay, I hope you understood well, because it is a very good question. Okay, now let's solve branch B. The branch B says the moment of inertia of the wheel. Moment inertia of what? Of the wheel. Okay, let's open a new slide. As you know, so it was a wheel. Okay, fix it on this incline. Okay, if you remember, this is the Ft. Okay, Ft, Ft tension force that acting on the edge of this wheel. Okay, so what is this? This is R. The radius of the wheel was given. Okay, radius of the wheel was given 0.1 meter. Okay, 0.1 meter. And what is the moment of inertia of this wheel? Okay, so in that case, to find the moment of inertia, we cannot use I is equal to 1 over 2m r squared, because the mass of the wheel does not given. Be careful, this mass, this is not the mass of the wheel, this is mass of the object. Be careful. Don't write mass is equal to 12 kilogram and time is 0.1 square. This is a big mistake. Be careful. So in that case, because mass does not given for the wheel, so that is why we have to think another equation. Okay, Newton second law for rotational motion is equal to net torque is equal to what? I alpha. Okay, so what is unknown? Moment of inertia. You have to rearrange equation, because the angular acceleration with the moment of inertia, so that is why it goes to the denominator. What is remaining in the numerator? The net torque. Okay, so the torque that acting on this wheel, we have force and the distance from axis of rotation, so that is why is equal to Ft times d, or Ft times r. Ft times r. Fr is the torque that acting on this wheel. Okay, and we don't have alpha, but instead of alpha we have acceleration, and r, as you know, A is equal to what? Alpha r. What about alpha? A over r. Instead of alpha, you can write down the tangential acceleration that produced by the wheel divided by the radius of the wheel. Now replace. Do we have tension force? We didn't have this force, but we found it in branch A, which was 47 times r 0.1, 82 divided by 0.1 is equal to 4.7 divided by 20, and I is equal to what? Is equal to 0.24 kilogram, 0.24 kilogram meter square. This is the moment of inertia for what? For the wheel. Okay? It's a very good question. Be careful, please. And so you have to solve this question after I solve it, okay? Now, let's go back to the question. Branch C, the angular speed of the wheel 2 seconds after it began rotating from rest. So we have to use the for kinematic equation. Omega final is unknown. Okay, to find omega final, because the angular displacement is not given in this question, so that is why we have to use this equation, omega final, omega initial plus alpha t. Omega final is unknown. Omega initial 0, why? Starting from rest. 0 plus alpha, we didn't have alpha, but we found it, which is equal to 20 times t 2 seconds. Alpha is equal to what? A over r, A2, r 0.1, sorry. 2 divided by 0.1 is equal to 20 times by 2. Omega final is equal to 40 radian per second. 40 radian per second. Okay? Let's go to another question. Question 39. Look at this question. Very good question, please listen carefully. So we have this node that related with the question 39. If an object starts rotating from rest and then stops because of the air resistance, of the friction, or any other reason, in that case, because the first time the object is start rotating from rest, this is speeding up. Start rotating from rest, it means that omega initial is 0. But for the second time, omega final 0 and final angular speed of the first case of the speeding up is equal to the initial angular speed for the second case. In this question, look, the combination of an applied force and the frictional force, this is applied force, okay? This is applied force, sorry, okay? This is applied force that acting on this object, okay? It goes to rotating from rest, omega initial 0, okay? Produces the constant torque 36 Newton meter, okay? Because the object start rotating, okay? On a wheel rotating about the fixed, the applied force acts for 6 seconds. Time is equal to what? 6 seconds, okay? During which time the angular speed of the wheel increases from 0 to 12. Omega final, it becomes what? 12 radian per second. This wheel, okay, rotating with the applied force, the combination of the applied force and the frictional force. In the first time, the wheel start from rest. What do you mean by start from rest? Omega initial 0. After 6 seconds, this is omega initial. This is omega final, 12 radian per second. After 6 seconds, it is angular speed increases and it becomes what? 12 radian per second. So what is this? This is speeding up or slowing down? This is speeding up. Okay? The force is still applied on the wheel. When the force is removed, what happened to the wheel? It stops. Okay, look. The applied force then removed. What happened when the applied force is removed on the wheel? The wheel tried to slowing down because of the friction of the air resistance. Okay? The wheel comes to what? To rest. What do you mean by comes to rest? Omega final 0. So what about omega initial in the case of slowing down is equal to the same final angular speed of the first case, 12 rad per second. Okay? So in the case of slowing down, omega initial is equal to what? Is equal to omega final of the first case. Because at 12 rad per second, the object starts to slowing down. Okay? Omega initial 12 radian per second. Omega final 0, it becomes to stop. In how many seconds? In 65 seconds. What is this? This is slowing down. Okay? We have two cases, speeding up and slowing down. The speeding up occurred in only 6 seconds, but slowing down, it takes more time, 65 seconds. Okay? Answer the following questions. A, what is the moment of inertia of the wheel? What is unknown? What is the moment of inertia of the wheel? I of the wheel is unknown. Because mass does not given in this question, so that is why we cannot use 1 over 2 mr square. Sorry. Mr square. We cannot use this equation. Why? Because we don't have mass. Okay? So, we have to think about another equation. Newton's second law for rotational motion. Torque is equal to what? Is equal to I alpha. Torque is equal to what? I alpha. What is unknown? Moment of inertia. Moment of inertia is equal to what? Moment of inertia is equal to torque divided by alpha. Okay? So, do we have torque? Yes. 36. Do we have alpha? No. Alpha is equal to what? Omega final minus omega initial divided by T. Now replace torque 36 Newton meter. Omega final in the case of speeding up 12 minus 0 divided by 6. 36 divided by 2, which is equal to 18 kilogram meter square. What is this? This is the moment of inertia of the wheel. Okay, so in that case, we have to find the moment of inertia of the wheel by using the speeding up given values. Okay, because in the case of speeding up, the torque is positive and the moment of inertia is always must be positive. How can you determine the moment of inertia? By using the speeding up. Why? Because in the case of the speeding up, the net torque was given. Without torque, you cannot find the moment of inertia. The second unknown, what is the frictional torque? What is what? Frictional torque. The torque of the friction is equal to what? It should be negative. Why? Because frictional torque is always, because the friction is always, it goes to slowing down an object. In the case of slowing down, angular acceleration is negative and and net torque is also negative. Why the net torque according to frictional force is always negative? Because of the friction, the frictional force, such as the air resistance of the friction between the objects and the ground, it goes to slowing down the object. So the slowing down, alpha is negative and net torque is also negative. Okay. In that case, the force is removed. Only the gravitational force or the air resistance affecting on the wheel, it goes to slowing down. Okay? So, the moment of inertia in the first case also equal to the moment of inertia of the second case. Why? Because moment of inertia does not depending on the angular acceleration and the torque. Moment of inertia of the wheel depending on mass and radius. In the case of speeding up and slowing down, it is mass and it is distribution of mass around the center of mass does not change. So that is why the moment of inertia that we found in the branch A is equal to the same moment of inertia of the branch B, because the wheel's shape doesn't change during rotating because it is rigid body, and its mass also doesn't change. Okay, so do we have moment of inertia? Yes, we found it, 18 kilogram meter square. Do we have omega initial? Yes, 12 radian per second. Omega final 0, it becomes stop. In how many seconds? 65 seconds. Now we can find the torque according to frictional torque. Frictional torque is equal to what? Is equal to I alpha. I is equal to what? 18. We found it, alpha omega final minus omega initial divided by T. This is frictional torque. Is equal to what? 18 times omega final 0, because the object stops because of the frictional force, minus omega initial 12. How did you know omega initial 12? Omega initial is equal, omega initial in the case of slowing down is equal to omega final of the case speeding up, divided by 65. The frictional torque is equal to what? Negative 3.3 Newton meter. Negative 3.3 Newton meter. This is the frictional torque of the wheel. Okay. Branch C. What's unknown in branch C? How many revolutions does the wheel make during the entire 71 seconds? What do you mean by the entire 71 seconds? It means that 65 plus, 6 seconds plus 65, T total is equal to 71 seconds. So what do you mean by the entire 71 seconds? It means that we have to find the number of revolutions during the speeding up or during the slowing down, both of them. But if the question says, how many revolutions does the wheel make during 6 seconds, the first 6 seconds, we have to use only the value that given for the speeding up. What about how many revolutions does the wheel make during the 65 seconds? We have to use the given value for the slowing down. Okay? How? Look. For the first one, for the first time, for 6 seconds, slowing down. In the first 6 seconds, the wheel is, speeding up, not slowing down. Speeding up. Speeding up from omega initial 0 to omega final 12 in how many seconds? In 6 seconds. How many revolutions does the wheel make in this 6 seconds? Theta during during speeding up. During what? Speeding up. Theta 1 is equal to what? 1 over 2 omega initial plus omega final times delta t. Theta 1 is equal to 1 over 2 omega initial 0 plus omega final 12 times 6 seconds. Half times 6 is 3. Theta 1 is equal to what? Is equal to 36 radian. 36 rad. Convert to rev divided by 2 pi is equal to what? Is equal to 36 divided by 5.7. Theta is equal to 5.7 revolution. During what? During speeding up in 6 seconds. The second angular displacement in revolution during what? During slowing down. The second time is what? During slowing down. How long did it take for the slowing down? 65 seconds. During the slowing down, omega initial 12 radian per second. Omega final 0 because the wheel stopped it after 65 seconds. In how many seconds? 65 seconds. So this is during slowing down. How many revolutions does the wheel take? Theta 2 is equal to 1 over 2 omega initial omega final times delta t. Replace 1 over 2 times omega initial 12 final 0 in how many seconds? 65 seconds. Theta 2 is equal to what? Times 65 and times 12. 390 radian. Convert to what? Revolution. Because the question asked it to find the number of revolution. Divided by what? 2 pi. Theta 2 is equal to what? Is equal to 62.1 revolution. Okay? So, this is the unknown of the question? No. The question in branch C say, find the number of revolution in the entire 71 seconds. It means that both speeding up and slowing down. Theta total is equal to what? Theta number 1, sorry, theta number 2. Total angular displacement in revolution. Theta number 1 during speeding up, which was 5.7, plus theta 2 during speeding up, which was 62.1. So theta total in 71 seconds is equal to what? We have to add up these two numbers, okay? Plus 5.7, 67.8 revolution in the entire 71 seconds. If you see this question in the Wizari exam, but if the question says how many revolutions does the wheel make during the 6 seconds, this number is correct. How many revolutions does the wheel make during the 65 seconds, which was slowing down? 62.1 is correct. But if the question says how many revolutions does the wheel make in the entire 71 seconds, we have to find the theta total, which is equal to 67.8 revolution. I hope you understood this question very well, because it is a very good question. Okay, look, 67.8 revolution during the entire 71 seconds, and I indicated very well here, as you can see. Okay, theta 1 over 2 omega initial omega final replaced during the 6 seconds. What do you mean by during 6 seconds? It means that speeding up. What about 65? Slowing down. What about 71? Both speeding up and slowing down. Okay. The last question that related with the Newton's second law for rotational motion, question 40 from chapter review. As I told you at first, we are going to solve the entire questions of the chapter review during the explaining, because this question is related with the Newton's second law for rotational motion, so that is why I solve it here. Okay, it means that when we are finished with this chapter, we already solved the entire and the all questions of the chapter review. Question 40, a cable passes over a pulley, okay, over a pulley that rotates about a fixed axis. Because of the friction, the force in the cable is not the same on opposite side. How many forces do we have? 2. Ft1, Ft2. 2 force, okay? This is Ft1, this is Ft2. Okay, this force produces counterclockwise torque, which is positive, but this force produces the clockwise direction, which is negative. Okay, how many force do we have? 2 force. It means that each force produces torque. This is clockwise torque, counterclockwise torque, and this is clockwise torque. So both the forces acting on this edge of the pulley, so this is R2 and this is R1. Okay, so in that case, R1 is equal to R2, the same thing. Why? Because we have 2 force in both sides. This is R1 and this is R2. The force on the on one side is 120 Newton. Okay, this is 120 Newton Ft1, and the force on the other side is 100 Newton. Assuming that, so in that case, the object is rotating like that, and the object is moving downward because this force is bigger. Assuming that the pulley is uniformly sick with a mass 2.1 kilogram and radius. So this radius, this is R1 and R2. R1 for Ft1, R2 for Ft2. This is R2, this is R1, and both of them is the same. Determine the angular acceleration of the pulley. How can we determine the angular acceleration of this pulley? Newton's second law, I alpha. Angular acceleration is unknown. Net torque divided by moment of inertia. How many torques do we have? 2. Why? Because we have 2 force. two force, opposite direction, opposite torque, it means that, okay, clockwise and counterclockwise with different force, is equal to what? Torque number 1, okay, plus torque number 2, divided by what? Pulley is equal to 1 over 2 mr squared, because the shape is pulley, because of the pulley, this has the shape such as a D6, so that is why we have to use 1 over 2 mr squared, okay? Now, torque 1 is equal to Ft1 d1 minus Ft2 d2. Why? Because F2 produces what? Negative torque. Why negative? Because it is clockwise direction, okay? Divided by 1 over 2 mr squared. Now, replace the number, okay? Ft1 120 times 0.8 minus 100 times 0.8. This is R1, this is R2. As I mentioned, they are equal. Divided by 1 over 2 times mass of the pulley was given 2.1 kilogram times 0.8 square. Angular acceleration for this pulley is equal to what? 24 radian per second square. Okay? So this is the angular acceleration for this pulley. Okay, that's all for today, and we finish it. The Newton's second law for rotational motion in chapter 2, section 3. Inshallah, in the next lesson, we will explain the angular momentum and kinetic energy for rotational motion. Thank you for listening. See you again as soon as possible, and keep up your best doing, and you have to solve all questions that I solved here.